So this pretty much goes over what we did yesterday, right? So we have to find the amount of moles. So there's 0.12 of H plus. And then we multiply this, and there's 0.15 of F minus, correct? That makes how much acid? 0.12 HF. Is there excess F minus? Yes, there is. And it is what? Is this going to be a buffer? Yes, it's a buffer. So what math would we use? Henderson Hasselbalch, right? Yeah, David Hasselhoff is fine. All right, so we take the pH will equal the negative log of the Ka. And so, like we said at the start, this is here just to trick you, okay? We made this acid from this acid, but HF is the thing that will be the boss in this. So we take the negative log of 6.5 times 10 to the negative 4, plus the log of B, which is this one, 0.03, over A, which is the one that's the acid. And there you go. And you end up with 3.59. 2. Oh, great. How am I going to lie here? $2.59. Who had that right? Okay, that is like a third. Does it make sense though? Okay. No, I think everyone tried it. If you switch this, is that what you did, Hunter? Did you switch this? Oh, sorry. When I started writing this, I thought I heard you go, oh, crap. Oh, okay. Well, that would be a problem too. Okay. Okay, well, moving on. This?
So 1.15.
Okay, now I had this short discussion with Isaac earlier. These should technically be concentrations, but in a buffer it's nice because they're all in the same volume. So if we like divide by 3 up here and we divide by 3 up here, it doesn't matter mathematically. Does that make sense? Or it was 4, I guess. All right. So anyway, moving on. That's that. Okay, next. Is this one a buffer? Yeah, don't overthink it. It says it's a buffer. So you're off to the races. It has 0.4 moles of formic acid, so there's your A, and there's the B, right? Now, be careful, because a lot of kids try and force this math into this problem. Here, you're not making a weak acid and having excess. It's already done, okay? So we just take this. We're going to use this one now. It asks the pH. It's the negative log of that Ka, 1.602, times 10 to the negative 4th, plus the log of B, which it just gave you was 0.6, over A, which it gave you was 0.4. Okay? Don't find the difference and do the math that you did here, because the chemistry is already done. So what did we end up with on A? 3.97. I waited that time to hear like very clearly. 3.97. How did that go? Who had that one right? Okay, that's at least 80% of you. 85%. All right. Letter B. Letter B, this is from an AP test. Like, both of these are sort of-ish from AP test, but this is an exact B off of test. You can tell because I never type my numbers that accurate. If 100.0 milliliters of this buffer solution is diluted to a volume of 1 liter with pure water, the pH does not change. Discuss why the pH remains constant on dilution. Okay, well that's pretty cool. Of question. The reason why is because the concentration of something, all right, and the Ka or Kb, it's like the amount per liter. So if you have 1/10 of a liter, the percentage or concentration will still be the same. If you have a liter, the concentration will still be the same. So even if we add more water, well, then more of it dissociates to maintain this constant value. Okay? So we could have 100 of these, and it wouldn't matter, like 100 liters, because as we add more water, the same amount will dissociate to constantly maintain that value. Well, it's anything, its solubility really is independent on the volume. Okay, a certain amount will dissolve per liter, per milliliter, per 1,000 liters. What? It was always going to be the same. More water, more dissociates. Does that sort of make sense? Okay? All right, now, letter C, it refers back up to A. Okay? What is the pH after the addition of 50 milliliters of HCl? So we're going to take this buffered solution and we're adding acid. So it's still pH equals negative log of 1.602 times 10 to the negative 4 plus the log B. Well, we have to convert these to moles, right? So I take 0.05 and multiply it by 0.5. Is that 0.025 or 0.25? Okay, 0.025. And that's the amount that the acid goes up and the base goes down. Are you okay with that? So the base was 0.6, 0.575, and then the acid is 0.425. And there's your new pH. .93. Now, there's not like a perfect way to check, but at least a way to check if you're super wrong. You added acid and the pH got lower. Is that good?
Yep.
Yeah. You did it right. Odds are, if you add an acid and you do the math and it went up, you just subtracted and added the wrong way. Does that make sense? Like you usually just did this 100% backwards. Okay, who had 3.93? Okay. Island, were you good on all of them? Those numbers look familiar. The first one was a little off? Okay, well, still good. All right. Awesome, right? Okay. There is more to chapter 17 than just buffers. All right. pH range, like these are just little nuggets here and there. The pH range is the range of pH values over which a buffer system works effectively. It is best to choose an acid with a pKa close to the desired pH. The range of a buffer is generally within plus or minus 1 of the pKa. All right, so it says what would be the buffer range for an acid if its Ka is 7.1 times 10 to the negative 4. So P, remember, just means negative log. So type this in. We take the negative log of 7.1 times 10 to the negative 4, and we get what value? .15. Okay. So it's saying what would be the buffer range? So it would be anywhere between 4.15 and 2.15. Whoops. That's all you have to know for this. Okay? The pH range. So like we wouldn't, if we wanted to stay around a 3.5, okay, we wanted to do a science experiment and maintain the pH to be around 3.5, then this would be a good buffer system to choose. It doesn't say what it is, but whatever it was, we could make that buffer and we would be within the range. But we would not choose a buffer that was like 5.6 times 10 to the negative 9. Like that'd be way off, and this would maintain a nice basic system, but it would be out of the range. Okay? a common test question, and I don't think I ask it, but I've seen it on the AP test before. It'll give you A, B, C, D, and E, and it'll all be different Kas, and it will tell you, like, you want to maintain a pH of 3.5. Which of the following would be the best buffer system to choose? So all you do is take the negative log of all of these, and the one that gives you the answer that's closest to the desired value is the correct buffer to choose. Is that fair enough? Okay. This is just more buffer math, like we did 1,000 of them. Okay. Some people have been waiting for information on titration for months. Who? The people that interviewed for the Sterling Scholar. All right? If you interview for a Sterling Scholar next year, I am going to ask you a titration question. And I'm going to say in all my years, 99.5% of humans have no idea how to answer it. It's just a buffer titration question. I can't tell you everything, but I'll tell you titration is one of them. And here's the deal. 99.5% of people have no idea what to do. And I know that. I know that. We're trying to see how you do when you don't know what to do. Because think of who applies for Sterling Scholar. They're G. All right? And this is the other half of the math in chapter 17 that's tricky, but it's not that bad. All right? In the titration, a known concentration of base or acid is slowly added to a solution of acid or base that is an unknown concentration. Okay? And it's been a decade, but we're going to do a titration lab. We'll either test how much vinegar is in vinegar, or we'll test how much acetylsalicylic acid is in an aspirin. Or maybe both. I don't know. We'll see. All right. So, in a nutshell, what we're doing, this says that this has HCl in it. All right? And this we have a probe in, so we could do some math. But pretend we don't. And we're going to say we do not know the concentration of HCl. Okay? A titration, like, we can figure this out pretty simply. Because if we know its volume, then we can do something pretty cool. When a solution is neutral, we know that the H plus is equal to the OH minus, right? So, if I don't know the H plus, but I can keep track of how much OH minus it takes to achieve neutral, well, that will tell me how much H plus there was in the first place. Let me say that again. If I don't know the H plus, but I do know that at neutral they're equal, then all I have to do is add base until the solution becomes neutral, and just keep track of how much and how concentrated a base I added. Do some math, and it tells me the H plus. The math for titration is as follows. And you'll notice something pretty quick. You take the volume of acid and multiply it by the concentration of the acid. And at neutral, or in a titration, that will always equal the volume of the base. I'm running out of room, so let's put vol, times the concentration of the base. And this is genius, because if you think about it, the unit for volume is liters. The unit of concentration is moles per liter. That equals the unit for volume, which is liters, times the unit for concentration, which is moles per liter. Mathematically, the liters cancel out, right? And if you look, it's just super genius. At neutral, the moles of acid cancel out to equal the moles of base, which that is the definition of neutral. All right, how do we know when it's neutral? All right, I think it's on this next slide. A pH meter or indicators are used to determine when the solution has reached the equivalence point. So we use indicators. All right, at which the stoichiometric amount of acid equals that of the base. So what we do, take our little thing, it's called a burette, and we're going to add it to our unknown acid. Okay, and in here, let's say it's like 2 molar NaOH. And down here, I don't know the concentration, but I do know that I have like 25 milliliters of this acid. You okay with that? So what I'm going to do now, I'm going to put in some bromothymol blue. And since this is an acid, it turns yellow. Okay with that? So now what I'm going to do, let me see, I gotta, oh shoot, we can do this. Okay, now what I'm going to do is I'm going to, there's a little valve here, I'm going to open this up and I'm going to add base to my acid. Okay, what's that? Oh, move this up. Okay, thank you. All right, now I'm going to stop doing this the moment that this turns green. Why? Because green is when this substance is at a pH of 7. Okay, so now I would just do some math. I needed to record where I started and where I ended. And let's just say I added 30 milliliters. You okay with that? The difference, we'll just say it took 30 milliliters to neutralize this. And now I'm ready, because it was a 4-variable equation, right? Now I have 1, 2, 3 out of the 4. So we're going to take the moles of acid, volume acid times the concentration. So 25 milliliters times my concentration equals 30 times 2. I was like, who is this human? Oh my. Is that all I am to you now? Life sucks when your AirPods are dead, I hear. Okay, so now, I now have 60 equals 25x. Man, I miss easy algebra. Divide both sides by 25, right? Well, this isn't the hard part yet. All right. 60 25ths is 12 fifths. So, I don't know that. What is it? And that would be 2.4 molar was my unknown concentration. Is that okay? Okay. Now, here we go. Here's a sample problem from your textbook. A 20 milliliter sample of 2-HBr solution is titrated with that. Calculate the pH of the solution after the following bases have been added. Oh, jeez. No, you do them one at a time, freaks. Well, when's the last time I made you turn in homework? Was it even this year? First try? Right before Christmas? So my Christmas present was like, no more homework? Yeah. Okay. So, this is, like, how did I lose you so fast? I know. It's Sarah. It was Sarah. See? All right. So, Hunter. Because Hunter was like, this isn't hard at all. Well, this is where it gets harder. Yeah. So here we go. We have A, B, C, D, and E. And yeah, we can do all of them. And it is not that bad. So here we go. We are going to, first off, is this a strong acid? Yes. Yes, I love my life. Listen, it's all of them from family 7 except for F. Okay? HCl, HBr, HI. And HAT doesn't make one. That's called HAT. Well, that's just synthetic ones that don't last very long, so don't worry about that. Okay, here we go. Okay, so what I'm going to do, I have 20 milliliters of 0.2 HBr. I don't give a crap about this in my pH world. So I'm going to take 0.02 liters and multiply it by 0.2 moles per liter, and I get what? All right, 0.004 moles of H plus. Okay, now we're going to use this number every single time because A, B, C, D, and E, we're not like saying, okay, we added 15. Now we're going to add 19.9 to that. We're just saying to the original. Okay, so here we go. 0.004 moles of H plus. In A, we add, and all of it is NaOH. Is that a strong base? Yes. So is any of this have anything to do with a buffer? No. And it doesn't have anything to do with weak acids or bases. So really, all we have to do in this is find the excess H plus, that was supposed to be a plus, all right, or the excess OH minus, and then negative log it. That's all we're doing. So here we go. In A, we add 15 milliliters of this. So I'm going to take 0.015 times it by 0.2, and I get 0.003. Everyone with me where I got that value? Okay, so for A, I subtract from this. You're always doing the math based on this. So 0.004 minus 0.003 equals 0.001 of what? Which one's excess? H plus. So I just take the negative log of that, and my pH equals 3. Because I learned logs a long time ago. Yeah, if this is a 1, then the log, all it even is doing, it's finding out how many places you move the decimal. That's all the log does. Now, we say it's finding the exponent, but if this is 1 times 10 to the negative 3, that's the same thing as saying take 1 and move the decimal 3 places that way. So that's all. But if this isn't a 1, I can't do the math in my head. I'm not that smart. I'm just that good looking. All right? Okay, sorry. That was awkward. So A was 3, right? Okay. I'm going to erase all this. I hate when I say gonna. I grew up in Myrtle. I said gonna a lot. All right. Now, so that wasn't bad. B, we're going to do the same process. Remember, we had 0.004 of H plus. In B, we have 19.9 milliliters of NaOH. Do the math. It's 0.0038, right? Do you know where I got that number? I take that, multiply it by 0.2. Oh, 398? Okay, thank you. All right, so I do the difference, and what do I get? Four O's and a 2. Okay, now, is this H plus or OH minus? That's H plus. Okay? And so now, if it's H plus, I take the negative log of that number, and it becomes my pH. .69 or 4.7. You agree with that? Okay. Everyone okay with that one? You're just simply finding which one is excess and you negative log it. Okay, C is a trick question to see if you're going to do any math. Because you don't have to. If you add equimolar amounts of acid and base, what's your pH? 7. Okay? Now, this only works because they have the same molarity, and then you add the same volume. You good with that? Okay, then D. Now we're adding excess base, right? This is now a bigger number. So we had 0.004. Now we take, and we pretty much have 0.0042. Why do I keep doing that? I feel like, because I'm ignoring the 0 right there. That's what I keep doing. Okay, now, you really always want to take the bigger number. Okay, because this needs to be a positive value. So you subtract now, and you're left with 0.12342 moles of what? OH minus. So now I'm going to do it slightly different. I'm going to take 14 and subtract the negative log of this number. Because now I'm finding the POH. .3. That makes perfect sense because this other one was 4.7 and it's the same difference. So, did they do the exact? Yeah, it's all right. We got 5 minutes. We got to make sure we do the hard one. I was just quoting what he was saying. Okay, do letter E by yourself. Because I feel like me doing 4/5 is like spoiling you. Everyone knows why it's going to rain today, right? There's a meet today. Soccer game today. I thought you had the week off for some reason. Okay. Okay. Yes. Oh, hold on. Be here. Half of you won't be. I'll probably give out a piece of paper with a few samples and just have you work through them. If I do that, I'll put the sample paper on Canvas as well.